So it's a great pleasure to introduce Susan Athey as the final keynote speaker of KDD 2015. So let me set the stage for our talk a little bit. Data mining, machine learning have been extremely successful, and they're powering, the online systems that we use every day, and all the way to enabling new types of scientific inquiry across many, many disciplines. And the data analytics that we provide is used to make policy decisions in an increasing rate. And that means what we're really interested in is finding interventions that have the most beneficial effects and estimating these effects of these interventions. Now, we've already seen on Tuesday in Ronica Harvey's talk how to do this in online systems, how to do these A/B tests in a very scalable and very robust and reliable way. But policy decisions and interventions span a wide spectrum, going all the way to, should we raise what's going to happen if we raise the minimum wage to $15? That's certainly something where we can't run easy A/B online tests, right? And there's a lot of different types of interventions all the way in between. Traditionally, this is kind of the domain of economics and econometrics, estimating effects of interventions and making predictions about interventions. But as Susan Athey's work has shown, there are lots of deep and interesting connections between the work that's done in economics and the methods that are developed there to the methods that we've kind of perfected in the KDD and machine learning communities. And Susan has really been one of the pioneers in exploring this space between econometrics, economics, and data mining. So it's a great pleasure to have her here today, and I hope that some of the things that she's going to talk about are also going to intrigue you that this is a very interesting area for doing research. So Susan is the economics of technology professor at the Stanford Graduate School of Business, and she's previously been faculty at MIT and at Harvard. And she has a long list of distinctions. I would just want to mention two of them. She is member of the National Academy of Sciences in the US. And the second one is that she got the John Bates Clark Medal, which for junior economists is the highest distinction that you can get. And it's probably the best predictor for eventually winning the economics Nobel Prize, but no pressure. So without further ado, Susan.
Thank you so much. It's a great honor to be here today. Of course, we all know that prediction is not a perfect science, so I don't feel too much pressure. It's really terrific that you all have been open to having an economist come, and I guess that you also had an economist in the closing session last year. Really, the connections between machine learning and economics have been really surprisingly slow to develop. So I came to it, I started working with Microsoft in 2007 on the Bing ad system, and I came to that because I was an expert in marketplace design and auctions. And that's where I encountered big data and machine learning for the first time. I was one economist in a sea of hundreds of machine learning specialists and engineers. And for the first couple of years, they thought I was a little crazy, and I thought they were a little bit crazy in terms of how we approach data and analysis. I quickly learned that I had better become bilingual if I wanted to get anything done, because there was one of me. And so it didn't matter how many prizes I had if I couldn't communicate, and then I wasn't going to be at all effective. So I had to become bilingual. And then I started trying to bring it back into economics. And really, for a couple of years, I've been giving talks and trying to explain what I had learned from machine learning and what I thought we could do differently in economics. And people nodded nicely, but I think they went back and whispered that I'd kind of gone soft with all that Microsoft work. But in the last year or two, there's really been a sea change in interest from economics, and I think it's just across all disciplines. We are also finally encountering the same thing I encountered when I first went to Microsoft, which was that my small data tools were just wholly inadequate. So the first kind of motivation to learn something new is just that, logistic regression and so on without any regularization, and it just blows up, and you can't do anything. And then Second, I think people are just starting to get on the part of the journey that I came through a few years ago, which is that, again, there's some things that we can learn that we're really not that good at in economics. So my research has been first trying to sort of import machine learning into economics, but also not just to take things off the shelf, but to try to confront directly the places where it doesn't perfectly fit. And so that's what I'm going to talk about today. My first audience for this research is to convince social scientists to use new techniques. But my second audience is all of you, because as I said, I hope I'll be able to convince you there's a few things that you want to do differently when you're asking causal questions or you're doing the kinds of analysis that economists are doing. And there's actually like one or two things about statistics that we actually know that you didn't. Which I know sounds really hard to believe. Now, the economists had the same reaction. How could we're the experts at working with data. Nobody asked a machine learning person about the minimum wage. They ask us. We're the cool guys. So they're not so sure they can learn something. But I think that feeling can be even stronger in machine learning. Nonetheless, hopefully you'll take away one or two small things. So just as an introduction, to sort of first summarize kind of what my conclusions from the process of becoming bilingual, is that, from supervised machine learning, the non-parametric prediction methods is just, it's been an amazing set of advances and that's really the state of the art. And it's got a huge influence in a whole bunch of different areas. And one of the key things that comes out of supervised machine learning that is just amazingly completely absent from most of cross-sectional econometrics and a lot of other social science work is cross-validation for model selection, data-driven model selection. And so that's one of the key themes from when I lecture to economists to say, we got to start doing that now. Also, there's some weaknesses. So, of course, there is a subfield of machine learning that focuses on causality, but it's not very well connected to, say, the rest of supervised machine learning. And again, I meet lots of PhD students at Stanford and from statistics and computer science who really can't well articulate, why you would even care about causality or why that would change the way that they do their work. On the other side, econometrics, social sciences, and parts of statistics, sort of the non-machine learning part of statistics, if you like, think a lot about causality, and in some sense that could be sort of a defining feature of econometrics. And we think about it in a couple of different ways. The first way is that we build sort of structural models that predict what happens when the world changes. And so I'm not going to present that today. That was some of the work that I've done, the first work I did with Microsoft Search Data, like modeling advertiser behavior. They're used for auctions, they're used for antitrust, and in business decision making, like especially pricing. So, a big auto company might hire an econometrician to figure out how substitutable different products are and how you should set the prices for their cars. All the packaged goods companies have teams of econometricians who build those kinds of models. These are probably the closest link in machine learning would be like latent variable models, LDA, and so on, because there you're trying to kind of get interpretable models that have some underlying features for the world. But we focus almost entirely on how to use these models to make predictions about what happens when the world changes. So if Staples and Office Depot want to merge, the Department of Justice will hire an econometrician to go out and predict what would happen when the world changes entirely. And so this is an important point when we talk about counterfactual predictions, because we are, in economics, we are absolutely not talking about having a holdout sample and trying to do a good job fitting there. That is not the question, because we have never seen Staples and Office Depot merge. So, there is no holdout sample. We have to make predictions about something fundamental changing. That is, what happens if the relationship between prices and features of consumers and so on changes fundamentally. So when I first I had a long time actually arguing with my first set of machine learning colleagues about this. And when I finally explained to them and found the right language to articulate this, that we were talking about what happens when the underlying stochastic process changes, and no, I can't just retrain my model, then they told me, wow, you're not a scientist. Like, you can't do that. That's impossible. And so I think that is actually what econometricians have worried about for like the last couple of decades, is what to do in this impossible situation where you don't actually have the right training data. And the key to doing a good job there is you really need to get causal parameters. Correlations aren't enough. You need to understand what causes a consumer to buy a car to understand what would happen if I released a new model, okay, or what if I took a model away. So I'm not going to talk about those more complex models today. I'm going to talk about mostly the same kind of question, but in maybe simpler examples where there's just sort of a binary treatment, like raising the minimum wage or releasing a new algorithm in search. But it's like one algorithm versus another is going to be the treatment. So, but all of this extends to these more complicated settings. So we have well-developed and widely used tools for estimation of causal effects in both experimental and observational studies. And for some parts of the policy world, believe it or not, machine learning does not have the highest market share. So like mergers, antitrust policy, labor policy, education policy, some parts of biostats are dominated by this other way of doing statistics. And the mergers are just now starting to happen. So some of the huge weaknesses, glaring weaknesses of this whole body of work is that they don't do anything systematic with model selection, and when we try to be non-parametric, we use things like kernels that kind of blow up very quickly with more than a couple of dimensions. So they just don't really even have much of a toolkit. And there's a few sub-literatures where this stuff comes together, but not a lot. So let me talk a little bit more about causal inference. So for causal questions, we want to know what would happen if a policymaker changes a policy. That's like, what if we administer a drug to a group of people? What if we change the minimum wage law or raise a price? And those of you working in tech firms, like actually the pricing problem is one where there's going to be the biggest interaction with econometricians. And there's a team of economists at Amazon that have been improving on the machine learning approaches they had, bringing in more and more from economics approaches, and they're finding much better performance with that. So the fundamental problem of causal inference, as stated by Holland, is that we don't see the same units at the same time with alternative counterfactual policies. So I don't see this, the same state with different minimum wage laws at the same time. And of course, that's also, and so randomized experiments that Ravi talked about is one way to try to deal with this. We're going to try to understand by doing randomized experiments. But we'll talk today about randomized experiments as well as observational data. So there's a bunch of different ways to express this. I'm going to use the sort of algebraic way. There's also, Perl uses sort of graphical models. First, the algebraic way of doing it has proved to be more convenient for certain types of analysis, so that's what we're going to stick to. So we're going to use this notation yi of w, and so that's the potential outcome function. And so I want to think of each of you as having a hypothetical outcome that you would have in different states of the world. So yi of 0 is what your temperature would be if you don't take the aspirin, and yi of 1 is what your outcome would be if you did take the aspirin. And it's a function, and I'm going to think about manipulating that w. In the demand context, I can think about w as the price. I can think about counterfactually, how much are you going to buy at, or what's your probability of buying at different levels of the price. And the price is something that I can manipulate. And of course, if I change my pricing policy, the relationship between price and all the other features will change. Okay, so I want to think about yi of w as being the fundamental relationship when I manipulate the price. And so we're going to talk a lot about binary treatments today, just to keep all the notation simple. So for a binary treatment, I can think about tau I as being the treatment effect, which is and every individual has their own treatment effect. So each of you is going to have a different impact of taking an aspirin. Could depend on how you're feeling today, what you ate, what your weight is, et cetera, et cetera. And those are generally going to be heterogeneous. We're going to think everybody has a different effect, and so we're going to think about average effects of that. Units of study also typically have fixed attributes or features. And so here I want to also just clarify that already this is an important distinction. In a lot of machine learning models, you just think about throwing all the features in together. You could easily think about W as being a feature, like price could be a feature in some sort of learning model. But I'm going to use different letters, one W for the things that we're manipulating, and X for the things that are, I think, of the fixed attributes of the people that aren't going to change. So like, I'm not going to contemplate moving coastal states inland when I change the minimum wage policy. I want to think about the attributes of the states as being fixed, and they're the consideration of the population. Okay. So I'm going to just briefly outline the research agenda and some of the directions, and I'm going to go into some depth on a couple of papers. So the research agenda that, like I said, for a couple of years I was out there just kind of saying, this is interesting, and these are the issues and the things we might work on. And then about 2 years ago, I finally said, you know what, like nobody's doing anything about this, let me give it a try. So I kind of dived in to try to do some of my own work. And so what were the things I wanted to do? Well, many problems in social sciences had this combination of prediction and causal inference. So I wanted to bring in machine learning tools, but I still want to test the hypothesis. For me, for any economist making a recommendation, I need a standard error. Like I need to know, I want to say, this is the effective price, and I need to have some sort of confidence interval around that. So I don't just need to, make a prediction. I need to have a sort of a parameter of the model that I'm estimating, and I need to know that that's asymptotically normal or something like that in order to do inference. So that's a challenge with some methods. And so, related to that, existing approaches don't directly apply to the problem of estimating causal parameters, and inference can be challenging. We don't know the properties of all the estimators, although in the last couple of years, there's also been a lot of progress on that. So some of the different types of things that I'm working on, first of all, just formally modeling the distinction between causal and predictive parts of the model and treating them differently for both estimation and inference. So I probably won't have time today to talk about this, but I have a paper, and I talked about it a little bit in the abstract for the talk, about actually how you do inference differently in environments where you are distinguishing between causal effects and attributes. So generally, for an economist, you run a regression. You would stick the W's and the X's all on the right-hand side of a linear regression or a logit model, and you can get parameter estimates and confidence intervals, and the mathematics of that would be the same for the W's and the X's. But I want to argue the math should be different. Why? Well, suppose like I see the data set of all the people who came to my talk today. That's my population, and whatever your attributes are, I could take all your temperature, and I could figure out the average difference between men and women in this room. And if I took all your temperature, I would know with certainty what the average difference in your temperature was at this time of day. But if I gave half of you an aspirin, gave you an aspirin and didn't give you an aspirin, I would not actually know for sure when I was done what would have happened counterfactually if I'd given all of you an aspirin. Because there's sort of missing data. For each of you, I only saw you in one state. So there's still uncertainty about the causal effect. And that's a different kind of uncertainty than uncertainty about the difference between men and women. Okay, and so part of this, a lot of the sampling, a lot of the literature on inference is based on sampling from a big population. But one of the observations I had when I worked with Microsoft, and that many of you should have when you work with your tech firms, is that you usually actually observe the whole population. You're not sampling. There's not like some hyperpopulation of Facebook users or something. You actually see data on all of them. And so how you even think about inference in that environment is a little bit different. But yet we don't necessarily know what would happen if I made a change from an A/B test, because I don't see everybody in each circumstance. So the second thing there's really themes, I've got a series of papers that incorporate both of these themes, is that my estimation methods want to combine with machine learning approaches and bring in the best of both worlds, what we learn from causal inference and what we learn from machine learning. And part of my challenge is going to be developing cross-validation methods that work. Because I love cross-validation, we should all do it, but actually it's totally not obvious how to do it for causal inference. Okay? So that's going to be one of my biggest themes. I'm going to show you that over and over again. But if I think about what I'm trying to figure out is the causal effect of giving you an aspirin, I don't observe that for anybody in this room. I ain't got no ground truth. And it gets even harder for things like price elasticities. and when I'm using some of our fancy techniques for dealing with endogeneity, we call it, or the fact that the price is not randomly assigned. So that's going to be one of our big themes, and I think that is something that could possibly interest this community, is that once I sort of pose the question, I'm going to give some answers, but like you guys have shown with every other method, the first answer is never the best answer, and they can be made better and better and better. So I hope that some people will be able to improve on my initial stabs at this. Some related things, we're also interested in robustness, again, because we're interested in parameter estimates. We're interested in things like a price elasticity. A price elasticity is how does demand change when you change price. We want to know how robust are our parameter estimates to alternative models. Machine learning is very good at generating lots and lots and lots of models in a systematic way. So that's something we've never figured out how to do in economics, is do robustness well. So I've also taken some initial stabs at that. Working some on network inference, as well as trying to make connections with LDA models and economic models. Okay. So let me now spend some time. I'm going to go in the most detail on this paper, and then I'm going to talk about a couple related papers that build on this. So the first motivation starts with actually A/B tests and experiments. So when we do experiments generally, we generally say you're going to have to say in advance how you want to cut your data if you want to do valid inference about what happens in subsamples. So actually, it's not just bad, but basically illegal if you're against policy. If you're a drug company and you do a large-scale test of a drug, you need to say in advance, I'm going to cut it by men and women. I'm going to cut it by decades of age. That's my pre-analysis plan. And if I find in my data later that this drug is super good for people from 70 to 75 that live in the South, doesn't matter. FDA won't accept it. It wasn't in your pre-analysis plan. And of course, why is that? Well, actually, in economics, data mining is a bad word. We've had to redefine it. So what we meant by data mining, what we used to mean by data mining, was the process of looking at your data and finding some little group of people for whom the thing had a positive effect, and then getting a really big t-statistic for that, pretending you never searched your data in advance, and publishing the paper. So that is, since drug companies have a financial interest in that, they have prohibited it. And there's actually been calls in the rest of social sciences as well to prevent you from data mining your experiments. Now, of course, when you have lots and lots of covariates, it's sort of ludicrous that you would think in advance about all the interactions among all the variables. So this is obviously extremely limiting for the progress of science. So what we'd like to do is have systematic methods that allow us to do data mining of experiments, but still conduct valid inference. Second, we just want to get heterogeneous treatment effects. So we're doing personalized medicine, personalized offers, and so on. We want to just understand how treatment effects vary by different individuals. So in a little bit later, I'm going to talk about actually directly estimating optimal policies. First, I'm going to just focus on measuring treatment effects themselves. And here are the ideas. You might want to do one experiment or do one big analysis to learn about the benefits of a drug or the benefits of a policy. The prices, the costs may change in the future, but you want to have a really precise estimate of the benefits that you can kind of hold in your mind for the future. And the math is going to be similar, but a little bit different when you're trying to actually directly choose optimal policies. So the basic outline is that we're going to again distinguish between causal effects and attributes and estimate treatment effect heterogeneity. We're going to introduce and analyze new cross-validation approaches for causal inference, and then get valid confidence intervals at the end. So I'm going to do all of this in the context of regression trees, which of course everybody here knows. The reason I'm starting with trees, you're going to see, is going to make it really, really, really easy to do inference. And because I'm trying to convince economists to do this stuff, and trees are really easy to understand. There's not some big black box behind there. If you have a leaf of a tree, you understand what's happening within that leaf. But in future work, we want to extend in some other to other more robust methods. Okay, so I'm just going to write down what everybody knows, the components of regression trees. And then I'm going to highlight in red here the pieces that I'm going to change when I go to do the causal inference, okay? So the standard tree, there's like, you're going to build the tree, and within a leaf, you're going to have an estimator or a predictor for outcomes, which is just the sample mean within the leaf. So that's component 1 of the model. Component 2 is the in-sample goodness of fit function, or the splitting function. And you're going to split a leaf according to the mean squared error. So you're going to, one split's better than the other if it improves the mean squared error of your predictions of y, your outcome. And then when we do cross-validation and out-of-sample goodness of fit to tell us how to prune the tree, we're also going to use mean squared error as a criterion. Okay. All right, so now I want to move on and think about trying to use trees to estimate causal effects. And I'm just reminding you of this model here. Again, the yi observed is going to be the yi as a function of the treatment that you received. And so if you received the high treatment, it's going to be yi of 1. And if you received in the control group, it's yi of 0. So you can think this is also like a partial label problem in classification. I only see that there's, in principle, we could know something about if all the different treatments, but I only see you with one treatment at the time. And so I'm going to mostly talk about random assignment of W for this paper, but I'll deviate from that in a few places. So what I'm trying to predict is individualized treatment effect, and again, this isn't observed for any individual. So it's not clear how to apply standard machine learning tools directly because I don't actually have a measure for my objective. So just to kind of to make more clear what we're trying to do, we can define mu of Wx as the conditional expectation of y given W and x. So in principle, again, if you didn't distinguish between W and x, you could just throw any kind of supervised learning at that and estimate mu. Tau of x would then just be defined as the difference between mu of 1x and mu of 0x. So if I wanted to just, take standard tools, there's two obvious ways to do this. And in the small subliterature of machine learning that's tried to think about this, both of these approaches other people have also thought these were the obvious things to do. A few people have tried this. So first, I could just analyze two groups separately. So I could say, okay, these are the guys who got the aspirin. These are the guys who didn't get the aspirin. I could build a tree or a forest or whatever else on one group and a tree on the other group. And then I can construct the predictions for each x and take the difference. Okay. The second approach is I could just put them all as features into one big learning model and go to town there. Of course, what you're going to see is if you're doing a tree and the tree doesn't split on the treatment variable from some parts of the tree, then you're going to get a 0 estimate of the treatment effect coming out of that. And so it's going to have this funny feature that you're going to have chunks of the population where you just predict a flat 0 for the treatment effect. And of course, that's not exactly what you wanted to do, which is why these things may not work very well. So the first approach is also got problems of building these two separate trees. So you think about what our goal is in supervised learning. What we're trying to do with the cross-validation and with the model selection is use our degrees of freedom in the best possible way. But if I build these two separate trees, what I'm telling my model to do is to predict the levels of your outcomes. And if you think about it, in most populations, like if I wanted to predict your weights or your temperatures, right, like say I took men and women, there are lots of things that would predict your weight and your height that have nothing to do with the treatment effect of an aspirin. And so there's going to be lots of covariates that would predict outcomes, and this is true in a lot of economic data sets. Treatment effects are often much less variable than just the level of your outcome. And so you're going to use all of your degrees of freedom trying to predict difference in levels when your whole goal is to predict treatment effect differences. So you're just going to have a very inefficient use of your data. But if I then said, okay, I don't want to do these approaches, I want to go straight at the treatment effect, I come back to the problem of cross-validation. So let me give you the first approach to estimating treatment effects directly. We're going to criticize this approach, but it's got one really good thing to recommend it, which is that it takes one line of code, and then you can throw any learner at it you want, and you'll get an answer out. So that's a positive feature for any model. So let me tell you how I'm going to do that. Turns out that if I just take one of you, I can just, for one person, with one person's information, I can get an unbiased estimate of your treatment effect. Okay? So I gave you an aspirin. I find out your temperature is 99. I can get an unbiased estimate of your treatment effect just with your data. Seems a little crazy. What's my unbiased? So suppose I did 50-50 experiment for my aspirin. My unbiased estimate for you is going to be 2 times 99. It's noisy. If I take Ronnie and his temperature is 98, and he didn't get an aspirin, my unbiased estimate of his treatment effect is going to be minus 2 times 98. Okay? So that's a crazy noisy estimate, but actually if I average up all of those estimates, it's going to give me the average treatment effect. Okay? So that's fairly straightforward. If you just do the math, I'm going to just say, okay, if I take the expectation of this y star being 2 times y if you got the treatment, and minus 2 times y if you didn't, and I take the expectation of that, that's going to average up to the treatment effect. Half the people are going to be positive, half will be negative, and I multiply by 2, and it all works out. So that's kind of interesting. Now, if it's p and not 0.5, I just readjust the probabilities. And if, in fact, I didn't have a randomized experiment, but I know there's some function mapping the covariates to getting a treatment, like it was some known function, it was an algorithm that took your covariates and put you into a group, not randomly, but by your covariates. As long as I can estimate that function, I can still normalize by that estimated function, and it's still going to work. So this is related to propensity score weighting, for those of you who are familiar with that. It's just actually, though, instead of thinking about propensity score weighting 2 different groups, I'm taking one transformed outcome. All right, so if I do this, then I can take any supervised learner and throw that transformed outcome at it. And now that supervised learner is going to be working hard to predict heterogeneous treatment effects instead of working hard to predict levels. Okay? So how would that work? Well, here I'm not actually changing any lines of code in my learner, but what the learner will do if I throw in my y star, the estimator for what happens within a leaf will be just a sample mean of yi star. I'll do mean squared error against the y star, and so on. So what are some problems with this? Well, it's really cool, not much coding. It does have a few problems. The first problem is actually if you look within a leaf, I'm going to kind of, if it was a 50-50 experiment, but it happened within my leaf, I was 55-45, when I estimate the treatment effect, I'll forget about it was 55-45 and weight them as if it was 50-50. So I'll just make a really stupid mistake, like if you had 55-45, you would take the average of the 45 and you would take the average of the 55 separately, and then take one difference minus the other, one average minus the other average. That's the best way to get the average treatment effect. This would accidentally kind of try to reweight them with 50-50. So you would get the wrong weights, and you would just have a stupid estimate of the average treatment effect. So the first modification we propose is not to be stupid and actually write a few lines of code, and instead of just taking the average of y star, readjust the weights to get the sample average. The second problem is a little more subtle, and that is that this transformed outcome, while an unbiased estimate of the average treatment effect, is actually quite noisy. And we may have better ways to actually deal with that. So in sample, what we propose is something that's analogous to using a Gini coefficient. We're going to say, well, in sample, if we're going to split a leaf, we want to split when I increase the variance of my treatment effect estimation. Just like the Gini coefficient, we're trying to increase the variance of the classification. I'd like to split when I increase the variance of my treatment effect estimation. And in expectation, it's going to give me the same thing as doing mean squared error. It's just going to be a lower variance way to get there. Out of sample, I also want to get rid of this high variance thing. And so here's something where we've got a proposal, but this is one where there's going to be 50,000 ways to do it, and there could be better ways to do it. So we proposed using single nearest neighbor matching. So for every observation, instead of using 2 times 99, I'm actually going to match you up with Ronnie, and I'm going to say, all right, Ronnie's the closest to you, So in terms of his feature space, and so I'm going to take the difference between 99 and 98, and that's my estimate of your treatment effect. And that's going to be a lower variance estimate of the treatment effect as long as there's someone close to you. Now, if I have 10,000 covariates and there's nobody very close, then I'm going to introduce bias. And so I'm going to have a trade-off between bias and variance reduction. The reason we pick one nearest neighbor is that among matching estimators, the one nearest neighbor minimizes the bias. And for cross-validation, we care a lot about bias. But what was shown in the simulation, but just theoretically, you can see the variance of this yi star. First of all, it's got a 1 minus p in the denominator, which is going to blow things up. But second of all, what the matching estimator is going to do is it's going to take account of differences in covariates. So if there's a lot of, if the x's really predict your outcomes very well, the matching estimator will help with that because I'm going to adjust for predictable differences in outcomes when I match you up with someone with similar covariates. And in principle, I could have a massive decrease in variance of this estimator. So to sum up the changes here, so my changes are in blue. So I want to say within a leaf, I want to take the sample average treatment effect. My in-sample goodness of fit function is going to be just a variance, saying again like a Gini purity score. And then I'm going to have out of sample, I'm going to have mean squared error. But since I don't observe the ground truth, I have an estimate of the ground truth, which I'm plugging in. And the other nice thing about this is that, the matching estimator, I can do it individual by individual, so every individual has a ground truth estimate in my out of sample. So then I can throw all this in and say, well, okay, now how do I think these are going to perform? So first of all, the single tree, two tree approaches will be more similar to causal approaches if treatment effects and levels are highly correlated. So if I say something about your age is going to predict your temperature, but it also predicts the effect of an aspirin, then I'm not losing much by making my models try to predict outcomes, because just by happenstance, that'll also predict heterogeneity and treatment effect. If they're very different, in which I think is much more common in practice, then they'll do badly. There's a few kind of polar cases where the separate trees will do very, very well. But those are pretty polar cases. The transformed outcome is going to do badly if there's a lot of predictable heterogeneity in the outcomes that we could control for with matching. So then we have to say, well, how do we compare the approaches? I'm going to use the oracle for simulation. One of the things we'll find in our simulations, luckily, is that other ways of measuring out of sample fit seem to line up pretty well with the oracle. So we do a simulation study. And first, at the top, we look at sort of how complex the models are. And one of the things we see is that the single tree and two tree, ST and TT, are much, much more complex than the transformed outcome tree and the causal tree. And that's because they're trying really hard to fit this variance in levels. The second thing we see is that the causal trees are more complex than the transformed outcome tree. And that's because the transformed outcome tree has a very high variance out of sample goodness of fit. So it keeps telling you, oh, your complex tree isn't doing you any good. And it's going to tell you that even if it is doing some good, because it's making mistakes in predicting goodness of fit. And then at the bottom, the oracle, we look at sort of what share of the time, the red circled numbers, what share of the time does the causal tree win and provide the better fit, and it does better sort of most of the time. And the different designs are just about varying how important level variation is versus treatment effect variation and so on. So the last piece of this is inference. So there's a conventional wisdom that trees are bad for inference because the trees are kind of discontinuous, and so things aren't going to be it's kind of hard to make them normally distributed. But here I want to highlight that the predictions are discontinuous in the tree, but we're not interested in inference in the tree structure. So the reason I'm going to use the tree and why it's going to be so easy for inference is that what I want to do is take, say, half the sample and use it to construct the tree, and then I can take the other half of the sample, and I can basically do analysis within each leaf of the tree. So I can, if I construct my tree, then I'm going to have a leaf, and if a leaf has 50 treated observations and 50 control observations, I can estimate the sample average treatment effect, and everything I know about how to calculate statistical significance will hold. And because the sampling variation that built the tree is going to be independent of the other sample, I'm going to just off the shelf completely obviously and simply be able to do inference. So this is kind of nice and it's easily interpretable. Now you might say, oh my gosh, you're throwing away half the sample. Isn't that terrible? Don't I have other methods that don't have this problem? But actually, that's not true. Like if you look at some of the papers that are doing consistency of random forests and so on, they also want to use one part of the sample to build the tree and another part of the sample to estimate, because it's actually just not true that you can get the right answer any other way. And even lasso, again, it looks all nice, but you have this nice asymptotic theory about lasso. But if you have, if your model's not as sparse as the number of observations you have, then you're going to get bias there too, because spurious sets of observations are going to lead you down the wrong path, and you're using the same data for selecting the model as you are for estimating, and you can get the wrong answer. So this, and I'm going to show you in a minute an application that even in a data set with 1 million observations and like 25 leaves, you'll get bias if you don't split. Okay. So let me give you this application now. So I looked at this in the Bing search engine. Queries are highly heterogeneous, and so we want to understand, how does the effect of various treatments vary with the type of the algorithm. So I did a specific experiment here. I had this kind of unique opportunity to do a large-scale experiment on the effect of position on clicks. So we really needed a clean causal effect here. The European Commission requested it. We were trying to understand what would happen if Google demoted their competitors. So we did this large-scale experiment, and we randomly flipped, say, the first and third position, the first and fifth position, and the first and 10th position to understand that, okay, things in the top position don't just click more because Bing does a good job ranking, but because of the position. So just focusing on the 1 to 3, the overall treatment effect we have is that you lose the 13.5 percentage points of clicking when you take the top position and put it in the third position. And then to try to understand, the effect of goodness versus the causal effect of position, we can compare the total you get when 1 goes to 3 to what happens naturally to the guy who's in the third position. So the dark blue is showing how many clicks the guy who's usually in the third position gets, and that's about 7%. So that 4.9% is sort of the how much better the first position link is than the third position. And of course, an A/B test allows me to get this causal effect. But now I might say, well, I can imagine, so we kicked out, by the way, the purely navigational terms like eBay searching, somebody searching for eBay, because first of all, the business didn't want to run an experiment like that because that's really going to piss off your users. And second of all, we also don't really think Google's going to take eBay and put it in the third position when you search eBay or anybody else. They might put up something else in the way, but they're not going to do that particular thing. But even within this, after we cut out the purely navigational things, there's a continuum of sort of how navigational queries are. So we might imagine the treatment effect might vary a fair bit. So this is some slightly modified data where we've pulled some things out to make sure that we're not revealing anything about our population. But we built a big tree to see how does the treatment effect of going from first to third position vary with features of the queries. And so just for example, over here, let's see if I've got yep. Over here we've got an almost zero treatment effect for things that were classified to be good fits for images and classified to be good fits for celebrities. So, if you search for a movie star, you don't really care about the algorithmic links, and there's therefore not a big effect of re-ranking them. On the other hand, some things that came out sort of high would be things that were classified to be likely to match up with a Wikipedia reference, more informational queries, where the ranking had even a much bigger difference than average. So we can go through and we see quite heterogeneous effects. On this slide, I've got each row is a leaf, and I've got the training sample and the training sample and the test sample, and I've got the treatment effects, the standard errors, and the proportions. And so I've highlighted in red some of the kind of small to medium-sized leaves that are where the training data has a more extreme estimate of the effect than the test sample. And overall, the variance in the training sample is like 2.5 times that in the test sample, which is just saying that even I've got actually like 500,000 in each, and I don't have a whole lot of bins here, so it doesn't seem like you're going crazy with the overfitting. But in fact, the training tree was finding some spurious stuff, because that's what you asked it to do. And when you go to the test sample, you're going to get more moderate effects. But here we'll get correct standard errors. And so just to think about an application of this, so if any of you are working on sort of large online firms, what you could think about doing is adding a method like this to your A/B testing platform. So if somebody does an A/B test for 2 algorithms, then what could pop up when they're done is this thing would produce you a nice little tree, and they could learn where their algorithm did well and where their algorithm didn't do well. And then perhaps you could, instead of saying, oh no, engineers, you can't roll out your algorithm because you did bad on average, I could just use the same features in here to trigger the algorithm on particular subgroups, and I would have statistically significant results without having to run another experiment. And we all know developers can be a little bit lazy in terms of analyzing their own data from the experiment. They might be more likely to just run a few more experiments rather than actually figure out what went wrong with their first one. So this could be a really useful diagnostic tool. And of course, similarly for personalized medicine. Okay. So the key to this approach is to distinguish the causal and predictive parts of the model, but then really try to use all your degrees of freedom to focus on your goal. And you know, the big sort of open question is how to do the cross-validation well. So I proposed something that did better than the most naive things, but we could improve on that. Okay, so there's a literature, a small literature that looks at some of these things. Independently of us, a few people have been working on, have tried this transformed outcome for lasso, which is something that is probably an improvement, and I definitely recommend people give a try to. But I still think the lasso could be improved upon with a transformed outcome by making better cross-validation criteria, because this is kind of a crazy objective, crazily high variance objective. And so extensions would be, you know, working on cross-validation criteria, optimizing for the case where you don't have a purely randomized experiment, and so on. So now let me take this to a second problem closely related, optimal decision rules, which can be framed as a classification problem. So for all the same motivations, and you know, we might not just want to know the average effect of an aspirin, but I might want to, in real time, actually assign people to take an aspirin or not. Very closely related, but a slightly different loss function, and so we're going to modify the methods a bit to do that. So same model. Now we're going to have an optimal policy, pi star, which would be that choice of, that should be a W there. The argmax over W of your, so we're going to figure out which treatment is best for you is a function of X. And I want to minimize the regret from the suboptimal policy. So this is similar to the other problem, except now I have a different loss function, not a mean squared error criteria where I'm trying to get low variance on the treatment effect, but I just want to get the right answer for people, but I care more for getting the wrong answer if there's a bigger difference in the outcomes. So there's actually a small literature here in machine learning about this from Begelsheimer and Langford and some of their co-authors. And the observation they had, which is actually similar to the one that we had on the regression side, is that we can actually just take an off-the-shelf classifier to solve this problem if we use cost weighting. And so what they suggest is to use cost weighting. If there was a randomized experiment, you would just take the outcome divided by the probability of getting that treatment. And so the result is that the loss from a cost-weighted classifier that tries to minimize misclassification error is the same in expectation as the policy regret. And so it's essentially like you're going to say, if I see you treated with an aspirin, I'm going to assume that's your optimal treatment, but I'm going to weight you more if you had a good outcome. I'm still going to, if you had a bad outcome and you gave an aspirin, I'm still going to assume that was your optimal treatment, but I'm just going to weight it less, and magically that gives you the right outcome. But it has a lot of the same problems as I talked about before because you've got this sort of high variance thing. So actually, I'm running out of time a little bit. So let me oops, the formatting didn't quite work on here. But anyways, let me tell you. I went into a little more detail about what Langford did. Let me just tell you a little bit about what we're recommending. So first of all, what we want to do is build a tree again, and within each leaf, we're going to estimate the treatment effect. But what we're going to do is do our splitting based on the policy regret. And so basically, if I say I had a leaf that was recommending everybody get treated, and now I do a split that some people get treated and some people are control, then I'm going to say the change in the policy regret is going to be the average treatment effect for those people for whom I changed my policy recommendation. And so I'm going to estimate that average treatment effect just using the sample average. Out of sample, for pruning, I'm going to similarly use nearest neighbor matching. And now there's going to be a little more of a divergence for every single individual. I'm going to estimate using matching your treatment effect, and I'm going to tell you one by one whether you were misclassified. And if you were misclassified, I'm going to penalize you by your estimated treatment effect. For inference, again, we can build the tree, and we can now just do a one-sided hypothesis test as to whether or not you got the right treatment, using one part of the sample for building the tree and one part of the sample for inference. So, basically the summary here is that using kind of a similar approach to what I suggested, with minimal coding, you can apply prepackaged classification tree to try to estimate what the optimal policy is. But you can possibly improve on that by using better cross-validation criteria that are designed to minimize variance and kind of take advantage of really solving the actual problem you were trying to solve. So we can think about online learning, explore, exploit. There's other directions to take that. So just in the last couple minutes, I promised to teach you something you didn't know before. So let me tell you about instrumental variables. So how many of you know what instrumental variables are? A few. OK, good. So the idea from instrumental variables is that you want to think about, what do I do if my treatment is not independent of the potential outcomes, even after I condition on covariates? And so what we do in economics is we use something called instrumental variables. And this is incredibly widely used. And any paper that ever tried to estimate the effective price would get laughed at if it didn't use this technique. Okay, so this is just completely mainstay for us. So some examples. So one of the classic papers was a paper that tried to look at the effect of military service on wages. You had all these people around the Vietnam War. Of course, whether you went to do military service in the Vietnam War is not uncorrelated with your potential outcomes. Okay? So a lot of people with good labor market opportunities did not go to fight in Vietnam. So what they did was they used this instrumental variable, which was the draft lottery number. So the draft lottery number was randomly assigned, and it was positively correlated with going to war. And because it was randomly assigned, it was uncorrelated with your potential outcomes. So you could think I could just pretend this was an experiment and analyze it as an experiment. So I could just run a model to understand the treatment effect of having a different draft lottery number. But that's kind of meaningless, because whoever cared about getting 10 points higher draft lottery number? That's not an interesting outcome. We're not going to ever do that again. What you really care about is the effect of military service. And so the way we deal with this is we project military service onto the draft lottery number and get a predicted outcome. And then we use the predicted outcome as the feature in the analysis. Okay, the predicted military service. So we're going to, in a linear regression context, we would regress wages on predicted military service. And so one of the reasons this is so interesting from a machine learning perspective is that we are going to decrease the predictive power of this regression. If I ran a regression and I put in whether you actually went to war on your labor market outcomes, I would do a better job fitting. If I had a holdout sample, that would fit better. But the going to war was correlated with your outcomes. It didn't cause them. If I use the instrumental variable, then there's a bunch of theorems that say I will get the average. It's a little complicated, but I will get a certain average effect of going to war. I'll get the average effect of going to war on those people who were shifted into war as a result of the draft lottery number. I'll never get the people who would have gone to war anyways. I'll never get the people who wouldn't have gone to war anyways. But for the people who were affected by the lottery, I can get their average effect. That's a theorem. But I'm reducing the predictive power of my model in terms of predicting wages. And so that's why we don't want to just cross-validate on mean squared error of the y, because that'll lead you in the wrong direction. The right direction for the causal effect of going to war is a less predictive model, but one that delivers a causal effect. Okay? So that really creates a challenge, though, if I want to think about doing cross-validation for this type of model, because it's even harder for me to come up with the ground truth in this type of environment, right? I had to make a lot of assumptions. I was doing modeling. Well, in this case, not a lot of assumptions. Draft lottery number was random. But often, you are making assumptions about your instrument. So it's much harder to get the ground truth. And so I'm working on this. I won't be able to tell you, I don't have perfect solutions to it. But this is really an open question about how you would do data-driven model selection for this type of problem. For the quantity sold on price, we often use things like input costs as instruments. And you get into this problem of weak instruments. So just to give you sort of one example that's maybe a little closer to home for this group, where I used instrumental variables to kind of show that what people were doing in practice was actually wrong. So, for click prediction, we might want to try to understand, it's very important, as you all know, for Google and Bing and so on, to understand the probability of click of an advertisement. And so the way we do this is we estimate a big supervised learning model. You've got clicks and you've got all the features, and you want to understand what's the probability different types of ads will get clicked. One of the huge determinants is position. So it's really important that your model do a good job understanding the effect of positions, because you might only see an ad in positions 3 and 4, but you're trying to ask counterfactually, what would happen if I got that ad up to position 1? That is a causal question. What would happen if I took this ad that I've never seen in position 1 and put it there? Okay? So what I could do is run here. I'm going to run a least squares regression. I could run a logit model, which is, they're very fancy versions of that is what used in practice. And we think that we get around, of course, we know that better ads are in higher positions, but we think we get around that by putting in advertiser effects and position effects. And we think we've soaked up that problem. So I'm going to show here that we haven't. So I ran a regression for iPhone and Viagra, 2 queries of indicators for being in each position. And so the ordinary least squares regression that doesn't factor in the fact that better ads are often in higher positions has a particular decay rate. This is the fraction of the top position clicks you get. So top position 2 is 66% of 1, and then 40, and then 04. So things drop off pretty steeply. So what I do is I use instrumental variables. So what are my instrumental variables? They're indicators for all the A/B tests that Bing ads happen to be running at that time. They weren't run for me, unlike the earlier experiment. They were just running. But each experiment is going to be good for some ads and bad for other ads. So for every ad, I predicted how being in a different flight was going to affect their position. And so that part of their position was unrelated to the user characteristics, unrelated to the match of the ad to the user, and was only determined by the A/B test. So I projected the position onto the A/B test indicators, and then I regressed clicks on the predicted positions. And so what I get out of that, this is the IV for instrumental variables, is a less steep decay curve, which is classic. All of our papers in economics, when we use instrumental variables, you do these 2 columns, one after the other, and you often get very different answers. And this is a classic kind of endogeneity problem, where we weren't, whatever indicators we were putting into this model, the OLS was not enough to deal with the fact that worse ads were in lower positions. And so only when we got a more random assignment of ads did we get a true decay function. So that suggests, if you were in a firm and you were trying to deal with this, maybe you want to do some true experimentation to learn about position effects if you don't trust my instrumental variables. But in any case, you could do something like this instrumental variables approach in practice. So this is, I think this is a really interesting thing that maybe to think about, since most of machine learning has never even really contemplated these kinds of problems. They do kind of really get at the core of the fact that we're about causality and not about prediction. And there's a lot of places where I think this comes together. Just as one example, the first stage of instrumental variables, where I project the position on the A/B test identifiers, that's a pure prediction problem, where we're already, one of the things we're working on is using machine learning methods to do a better job with that. So hope you learned something new at the very end. Thanks so much for listening. Please email me references that I missed. I'm sure I missed some, and I hope to keep in touch with all of you as this literature goes forward. Thanks.
I have two related questions. The major question is there any sort of systematic way to identify instrumented variables? And one specific instance that I'm having a hard time wrapping myself around is what if you need to get a second instrumented variable to accurately predict the first one and the third one to get the second one and so on and so forth?
Absolutely. So actually when you just have one instrumental variable and it's not actually randomly assigned, like the draft lottery or these A/B testing things, but it's something like, oh, I want to argue that input cost shocks are unrelated to consumer demand shocks, then you just argue. So economists spend a lot of time in seminars just arguing about their assumption. And in a lot of applications, you're lucky if you got one sort of good instrument. So you argue for a while. Now, if you want to be more data-driven, and in environments like online environments, you might imagine instead having lots of instruments that are each a little bit, they might all be valid, but they're weak. So this example of the A/B test, each A/B test actually only had a small effect on positions, but I had a lot of them. So there's a whole theory around what you do with lots of weak instruments, as well as tests, specification tests. So as soon as you have multiple instruments, you can use one to test whether the other one is valid, and it becomes more data-driven. So you're exactly right. So you should have been an econometrician. 20 years ago, you could have had a famous paper.
Very nice in their simplicity, but it's something in terms of predictive power that kind of we as a community are not using anymore. So what would be a wish list of for a method that you would like to use?
Sure. So I guess one thing about the trees is that this crowd doesn't use them very much. But like in the business world, more broadly, they are used by the business groups and so on to create segments and provide interpretability. So they're actually incredibly widely used. They're just not perfect at prediction. But yeah, so I mean, I think one of the things I'm working on is random forests. I want to, in lasso also have some consistency properties and potentially asymptotic normality properties. So generally, what the social scientists are going to want is something where at the end of the day, I can do a hypothesis test on my causal effect of interest. And that's really the thing. So there's been some recent progress on random forests, which I'm pretty sure we can use those, and I'm working on that now. And then, some of the more economists, actually, there's one economist at MIT with a couple of co-authors who's been pushing lasso. And it took him a couple of years to get traction. But I think that's likely to get the most traction because economists used to run a lot of regressions. And so it looks like a regression. And under some conditions, it's going to give you consistency and asymptotic normality of parameter estimates. The only thing I would say about that is it's a little bit slippery and misleading because the conditions are often not satisfied. And so, you're kind of fooling yourself a little bit. And so we need to work harder at making sure, it's one thing to do prediction, but if you want to really get a parameter estimate right, that's going to be affected by all the other parameters and what's been pushed to zero, and you're going to get biases. So that's understanding better sort of the asymptotic distributions of parameter estimates coming out of implicit or explicit parameter estimates coming out of all of these things. And it's kind of puzzling to me because I spent like the last month and a half reading all of these papers, and like asymptotic normality just doesn't come up as a keyword in this literature. And it's important to us. And so people use kernels, which, like, as you all know, like a multivariate kernel, does terribly in practice. But economists use it all the time because under some crazy conditions, a 100-dimensional kernel has asymptotic normality. So they prefer it.
Yeah. So there are some economists who build these sort of very detailed nonlinear parametric models, and I'm curious what machine learning techniques can contribute sort of in the spirit of your talk today.
Excellent point. So actually, so far, my research has been completely sort of separate. So my sort of parametric complicated models I've used for advertiser behavior, and I built a really large-scale Bayesian model. But I didn't actually, it looks kind of like a machine learning model, but actually just Bayesian statisticians are Bayesian statisticians. So actually, economic Bayesian statisticians don't look so different than machine learning Bayesian statisticians. They're just do all the same thing. Except you guys computed a little better. So, that helps. I would say, though, a couple of things there. One is that separating the components of the model can be helpful. So again, we might build a very detailed model of how you bid in an auction, but there's no economic theory to guide the functional form for all the different attributes of the advertisers. So one of the lines I'm pursuing now is to, again, combine this detailed structural model part with a lot of non-parametrics from machine learning to soak up all the variation in the advertisers. So it's a generalization of this heterogeneous treatment effects. Now it's going to be heterogeneous behavioral responses by advertisers. So I think that's one very fruitful alley. Another way, the stuff I'm working on with David Bly, I tried without him to do a large-scale recommendation system type thing for economics, and I can compute it. And so, the latent variable models look a lot like economic models. It's just that we put a little more emphasis on how the functional form affects the out-of-sample predictions and what in the data tells me that there's 10 unobserved attributes or latent features.